Hello, welcome back to the course of process control. Today I'm going to talk about the development of models for a process. In this video, I will explain the requirements and characteristics of models for process control. After completion of this session, participants are expected to be able to develop equations to represent processes in chemical plants. Let us commence with how mathematical models develop from abstraction. You may remember how a process was operated prior to advancement of process control, when processes were still controlled manually. To control such a process, experienced engineers make decisions based on their understanding of how a system will react under various changes. Such intuitive knowledge is acquired by observing the system over time, by making changes in the system and monitoring the consequences of these changes. This leads to an abstraction of the behavior of the system in the engineer's mind. This abstraction is effectively a conceptual model of the system. A more universal expression of the system is the use of mathematical relationships that explain the physical and chemical phenomena underlying the performance of the system. This gives us mathematical models. But what kind of mathematical models do we need for process control? In general, we want models which can rationally represent a physical system. For control purposes, we are particularly interested in the evolution of processes over time. Remember that the objective of control is to maintain desired levels of a process variable by manipulating another variable, all in the presence of disturbances. One can observe that all these variables are time-dependent, thus requiring a dynamic model to express the behavior of the process. To gain sufficiently accurate models, we also need to consider, aside from the fundamental knowledge about the process, the past experience and engineering intuition. There's also another aspect to consider when developing a mathematical model. How accurate we want our model to be will dictate the model. If we need to be precise, the model should try to accurately reflect all physical and chemical phenomena taking place in the process. This model usually stems from established theories and is called a fundamental or mechanistic model. On the other hand, if we are only interested in the general trend, a simple relational model may suffice. This model can be constructed from experimental data and is called an empirical or black box model. Between these two extremes, there are also models that combine both fundamental theories and empirical data. Such models are developed using known theories but only partially. There are many reasons for this. It could be that there is insufficient knowledge to complete the models, or the models are simply too complex. In such a situation, empirical data can be used to complete the models. Bear in mind that all real systems are complex. Building an exact description of a process is usually an impossible task. That's why we need to compromise between model accuracy and complexity with the cost and effort. Alright, before discussing model development, let us look at model classification. Classifications help us determine the difficulty in development and solution of model as well as design of associated control system. Our first classification is between linear versus nonlinear. An easy way to identify nonlinearity is to look at any multiplication involving the dependent variables and their derivatives. You can see in this example, the left equations are linear, while the right ones are not. Nonlinear systems are usually difficult to deal with, so they are usually linearized. We will discuss the linearization techniques later. Our next classification is between lump versus distributed parameter. Lump parameter systems ignore spatial variation. Because we do not have to account for the spatial variables, such systems can be expressed using ordinary differential equations, which are much easier to handle than partial differential equations for distributed parameter systems. An example of lump parameter systems would be the equation describing composition in a continuous stirred-tank reactor in which all element volume inside it is assumed to be uniform. An example of distributed parameter systems would be that of a plug flow reactor. Our last classification is between deterministic versus stochastic. Their difference lies in whether there are random elements involved. In deterministic systems, all values of variables and parameters will have fixed values. In stochastic systems, some values of variables and parameters will instead have range of values with some probability distribution. The control theory is well developed for linear, lump, and deterministic models. So we will always try to simplify or convert our models to these types. This is the end of this video. We will discuss the model development in next video.